Adjusting the magnetic trip setting on a molded case circuit breaker, specifically a Siemens 1000 amp breaker with an adjustable magnetic trip unit, directly impacts the level of magnetic force required for the breaker to trip in response to a short circuit fault. A higher setting necessitates a greater magnetic force for the breaker to activate and trip. Conversely, a lower setting causes the breaker to trip more rapidly. The range from 5,000 to 10,000 on the adjustable magnetic trip unit signifies the long time pickup or minimum trip current for short circuit faults. This range represents multiples of the breaker's rated current, which in this instance is 1000 amps, at which the magnetic trip unit will initiate a trip. The thermal and magnetic trip units both respond when a short circuit occurs. The thermal trip unit detects an overcurrent condition and, after a time delay, trips the breaker. This protects against overloads. The magnetic trip unit responds to the abrupt increase in current caused by a short circuit, tripping the breaker almost instantaneously. The magnetic trip setting dictates the minimum current level at which the magnetic trip unit will activate. Lowering the setting, for example, to 5,000, results in the breaker tripping more rapidly in response to short circuit faults, offering enhanced protection against damage caused by high current. However, this can also lead to nuisance tripping during normal operations or when starting large motors. Conversely, raising the setting, for instance, to 10,000 requires a higher current level to initiate a trip, which can mitigate nuisance tripping but might compromise the overall protection against severe short-circuit faults. Selecting the appropriate magnetic trip setting should be based on the specific application and the needs of the protected equipment. It is highly recommended to consult with an electrical engineer or refer to the manufacturer's instructions for guidance on the proper adjustment. Understanding the magnetic trip setting of a circuit breaker is crucial for ensuring effective electrical protection. The magnetic trip provides instantaneous protection against short-circuit faults, complementing the thermal trip, which offers delayed protection against overloads. The magnetic trip setting determines the level of current at which this instantaneous protection is activated. A lower setting provides more sensitive protection, tripping the breaker at lower fault currents. This is desirable in applications where sensitive equipment needs to be protected from even small short-circuit currents. However, a lower setting can also lead to nuisance tripping, where the breaker trips unnecessarily due to transient currents or inertia currents from starting motors or other equipment. A higher setting requires a larger fault current to trip the breaker. This can reduce the risk of nuisance tripping, but it also means that the equipment is exposed to higher fault currents for a longer period of time before the breaker trips. This can increase the risk of damage to the equipment. The range of 5,000 to 10,000 on the magnetic trip unit represents a multiple of the breaker's rated current, which is 1000 amps. Therefore, a setting of 5,000 corresponds to a trip current of 5,000 amps, and a setting of 10,000 corresponds to a trip current of 10,000 amps. When selecting the appropriate magnetic trip setting, several factors need to be considered. Firstly, the type of equipment being protected. Sensitive equipment requires a lower setting to provide better protection. Secondly, the potential fault current. The setting should be high enough to prevent nuisance tripping but low enough to provide adequate protection against short-circuit faults. Thirdly, the coordination with other protective devices. The magnetic trip setting should be coordinated with other circuit breakers and fuses in the electrical system to ensure that the breaker closest to the fault trips first. This helps to minimize the impact of the fault on the rest of the system. It is important to note that adjusting the magnetic trip setting should only be done by qualified personnel. Incorrect settings can lead to inadequate protection or nuisance tripping. It is also important to consult the manufacturer's instructions for the specific breaker being used, as the recommended settings may vary. In addition to the magnetic trip setting, circuit breakers also have other settings that can be adjusted, such as the long time delay and the short time delay. These settings affect the time it takes for the breaker to trip in response to overloads and short circuits. The long time delay setting determines the amount of time that an overload can be sustained before the breaker trips. A longer delay allows for temporary overloads such as those that occur when starting a motor without tripping the breaker. However, a longer delay also means that the equipment is exposed to the overload for a longer period of time, which can increase the risk of damage. The short time delay setting determines the amount of time that a short circuit can be sustained before the breaker trips. A shorter delay provides faster protection against short circuits, but it can also lead to nuisance tripping due to transient currents. The coordination of these settings is critical for ensuring the proper operation of the electrical system. The settings should be chosen to provide adequate protection against overloads and short circuits while minimizing the risk of nuisance tripping. The National Electrical Code, or NEC, provides guidance on the selection and coordination of protective devices. NEC Section 240.12 covers the requirements for selective coordination of overcurrent protective devices in industrial installations. Selective coordination means that the overcurrent protective devices are selected and coordinated to ensure that only the device closest to the fault trips, minimizing the impact of the fault on the rest of the system. The NEC also provides tables of conductor ampacities, which are used to determine the appropriate size of conductors for different applications. These tables take into account the conductor material, the insulation type, and the ambient temperature. Using conductors that are too small can lead to overheating and potentially cause a fire. In addition to the NEC, other standards and guidelines may also be relevant depending on the specific application. For example, the National Fire Protection Association, or NFPA, publishes standards for electrical safety in the workplace. These standards provide guidance on topics such as arc flash protection and electrical safety training. It is important to stay up to date on the latest codes and standards to ensure the safe and reliable operation of electrical systems. In summary, adjusting the magnetic trip setting on a circuit breaker is a critical aspect of electrical protection. The setting determines the level of current at which the breaker will trip instantaneously in response to a short circuit fault. A low setting provides more sensitive protection but can also lead to nuisance tripping. A higher setting reduces the risk of nuisance tripping but may compromise protection against severe short circuit faults. The selection of the appropriate setting should be based on the specific application and the requirements of the protected equipment. It is recommended to consult with an electrical engineer or refer to the manufacturer's instructions for guidance on the proper adjustment. Understanding the interaction between the thermal and magnetic trip units is essential for proper circuit breaker application. The thermal trip unit is designed to protect against sustained overloads, while the magnetic trip unit is designed to protect against short circuits. The thermal trip unit uses a bimetallic strip or other heat-sensitive element to detect overcurrents. When the current exceeds the breaker's rating, the bimetallic strip heats up and bends, eventually tripping the breaker. The time it takes for the thermal trip unit to trip depends on the magnitude of the overcurrent. Smaller overcurrents will take longer to trip than larger overcurrents. The magnetic trip unit uses an electromagnet to detect short circuits. When a short circuit occurs, the current rises rapidly, creating a strong magnetic field. This magnetic field attracts a lever or other mechanism, which trips the breaker. The magnetic trip unit is designed to trip very quickly, typically in a few milliseconds. This is important to minimize the damage caused by short circuits. The magnetic trip setting determines the level of current at which the magnetic trip unit will operate. This setting is typically adjustable, allowing the breaker to be customized for different applications. A lower setting will cause the breaker to trip more quickly on short circuits, providing better protection for sensitive equipment. However, a lower setting can also lead to nuisance tripping. A higher setting will require a high current to trip the breaker, reducing the risk of nuisance tripping. However, a higher setting may not provide adequate protection against short circuits. The appropriate magnetic trip setting will depend on the specific application. For example, a breaker protecting a motor may require a higher setting to allow for the motor's inrush current. A breaker protecting sensitive electronic equipment may require a lower setting to provide better protection against short circuits. It is important to consult with an electrical engineer or the manufacturer's instructions to determine the appropriate magnetic trip setting for a particular application. In addition to the magnetic trip setting, circuit breakers also have other features that can be adjusted to improve their performance. These features include the long time delay, the short time delay, and the instantaneous trip. The long time delay setting determines the amount of time that an overload can be sustained before the breaker trips. This setting is typically adjustable from a few seconds to several minutes. A longer delay allows for temporary overloads, such as those that occur when starting a motor without tripping the breaker. The short time delay setting determines the amount of time that a short circuit can be sustained before the breaker trips. This setting is typically adjustable from a few cycles to a few seconds. A shorter delay provides faster protection against short circuits, but it can also lead to nuisance tripping due to transient currents. The instantaneous trip setting causes the breaker to trip immediately when a short circuit occurs. This setting is typically used for very sensitive equipment that requires immediate protection. The coordination of these settings is critical for ensuring the proper operation of the electrical system. The settings should be chosen to provide adequate protection against overloads and short circuits while minimizing the risk of nuisance tripping. It is important to consider the characteristics of the equipment being protected when selecting these settings. It is also important to consult with an electrical engineer or the manufacturer's instructions to ensure that the settings are appropriate for the particular application. When working with circuit breakers, it is important to follow all safety precautions. Circuit breakers can be dangerous if not handled properly. Always disconnect the power before working on a circuit breaker. Wear appropriate personal protective equipment, such as gloves and safety glasses. Follow the manufacturer's instructions for installing and maintaining circuit breakers. If you are not qualified to work on circuit breakers, hire a qualified electrician. Furthermore, understanding the breaker's interrupting rating is key. Interrupting rating is the maximum short circuit current that a breaker can safely interrupt. This rating must be greater than the available fault current at the breaker's location. If the available fault current exceeds the breaker's interrupting rating, the breaker can fail catastrophically during a short circuit, potentially causing serious injury or damage. The available fault current can be calculated using engineering software or by performing a short circuit study. This study takes into account the impedance of the power source, the transformers, the conductors, and other components in the electrical system. It is important to have a qualified electrical engineer perform a short circuit study to determine the available fault current at each point in the electrical system. The interrupting rating of the breakers must be selected to be greater than the available fault current at their respective locations. Breakers with higher interrupting ratings are more expensive, so it is important to select the appropriate rating for each application. Using a breaker with an interrupting rating that is too low can be extremely dangerous. The label on the breaker indicates its interrupting rating. The label also indicates other important information, such as the breaker's voltage rating, current rating, and trip characteristics. It is important to read the label carefully before installing or working on a circuit breaker. In addition to the interrupting rating, the breaker's voltage rating must also be considered. The breaker's voltage rating must be equal to or greater than the system voltage. Using a breaker with a voltage rating that is too low can result in the breaker failing or causing a fire. Circuit breakers are an essential part of any electrical system. They provide protection against overloads and short circuits, preventing damage to equipment and injury to personnel. It is important to understand the principles of circuit breaker operation and to follow all safety precautions when working with circuit breakers. Consulting with a qualified electrical engineer is crucial for selecting the appropriate breakers and settings for a particular application. Regular maintenance and inspection of circuit breakers are also essential to ensure their proper operation and safety. This includes visually inspecting the breakers for any signs of damage, testing the trip function, and tightening connections. A well-maintained electrical system with properly selected and installed circuit breakers is essential for a safe and reliable power supply.